So yesterday in Miss Crenshaw's room, a leak started to form in the ceiling panels, and we decided to turn it into a math problem. So if we assume that the shape of the ceiling panel as water filled into it was a hemisphere, and the water level was here, we wanted to find the rate of change of the height of the water if the height is 6 inches. And the inflow rate is a total of 1.3 cubic inches per minute. So Zach's going to tell you about what we want to know and want in this problem.
So, because the water is flowing into a shape that is changing, it means that we have multiple variables, the radius of the hemisphere of water and the height of the hemisphere of the water changing at the same time. In order to understand how those two factors correlate, we need to set up what we call a related rates problem because the two factors are interdependent. So Jonathan and I just assumed that the radius of the hemisphere of water was 12 inches at a given moment. The height was 6 inches. And we also made the assumptions about the rates of water flowing into the panel and water slowly leaking out of the panel through a hole in the bottom. With that in mind, we wanted the change in height over time at the moment when the height was 6 inches. So over here, we established a formula for the volume of a cap of water, which would be just a small disk of water on the surface of that hemisphere. So here we have this diagram where capital R is 12 inches, and that would be the radius from the center of the hemisphere to any point along the edge. And then setting up this Pythagorean or this right triangle, we can use the Pythagorean theorem to establish that the radius squared equals 144, which is the capital R value, that's the radius of the hemisphere, minus 12 minus y squared. This red bracket right here is 12 inches minus y, which is the amount of water in the amount of water in the bottom of the hemisphere. From there, you plug that r squared value into the area formula for the area of a circle, and then rotated that 360 degrees using an integral in order to then prove this relationship and come up with the formula for the volume of a cap of water. Jonathan, you want to take it from here?
Yeah, so what we need to find now is the derivative of this volume because we want to find the rate of change of the height. So we took the volume of the cap, which we have written again here, and we derived it. We plugged in for dV dt, which we know is 1.3, and we plugged in 12 for our total radius. And after deriving this, we come up with this formula here. Pi over 3 times 72 height times h prime minus 3h squared times h prime. And then we plugged in values for that.
And that's how we got the rate of change of height over time.
Well done, guys.
All right.
Well done.